Hello, welcome to On-Ramp Feedback Metering by Luke Radcliff, Joseph Fahler, and Dylen Ziegler.
Problem statement. Chances are, if you have traveled in a car, you've experienced some sort of traffic delay. Traffic delays can happen anywhere at any time, but often occur during the work rush hours. This is especially true in the metropolitan areas. The image shown depicts the overcrowding of Philadelphia's I-95 highway this past summer as SEPTA strikes left thousands of commuters to travel to work via automobile when they would have normally taken public transportation. The overcrowding of highways and traffic jams is present in cities around the world. The National Highway Safety Administration claims that each year, the average commuter spends 41 hours sitting in on-off ramp traffic. Most individuals accept this as an unavoidable factor of their workday commute. However, this assumption is incorrect. The use of ramp feedback metering in heavily traveled areas can reduce traffic and travel time significantly.
Background. Ramp metering is a method by which traffic seeking to gain access to a busy highway is controlled at the access point via traffic signals. This control aims to maximize the capacity of the highway and prevent traffic and congestion. Inflow and density are directly related, but they have their difference, for inflow equals speed times density. Inflow is the number of vehicles passing a reference point per unit of time. Density is defined as the number of vehicles per unit length of the main line. Max density is the maximum density that the main line can sustain. Critical density is a set density below the max in which traffic density is to be stable at or never go past. Traffic is dependent on several variables. Freeway inflow is the flow of cars into the main line. Ramp inflow is the flow of cars onto the ramp. The length of the ramp. Freeway traffic density is the number of vehicles on the main line. Ramp traffic density is the number of vehicles on the ramp, or queue. Ramp metering also has various benefits. One is an increase in safety. A 6-year study along a 7-mile stretch of highway during the AM/PM rush hour in Seattle showed a 39% reduction in accidents. 2. Decrease in travel times. A 3-year evaluation of Long Island, New York, eastbound expressway showed an average motorist travel time decreased by 13%, with the average speed increasing from 29 to 35 miles per hour. 3. Reduce fuel consumption. A study in Portland, Oregon along I-5, a large commuted highway, reported that fuel consumption was reduced by 540 gallons of fuel per workday.
Modeling. Here we have pictorial representation of the inputs, outputs, and components of a simple feedback ramp metering system. First is the mainline traffic flow F of T. This can be represented as the cars that are already a part of the mainline traffic flow. Next is the ramp inflow R of T. This is the cars entering the highway ramp from other areas and roadways. These cars will then begin to exit the ramp onto the freeway. We will call this ramp outflow U of T. However, not all of these cars will be able to merge at a steady rate, so we will place these cars in a ramp queue called L of T. It is assumed that the vehicles in F of T and U of T will merge together along the distance delta X and create a density rho of T. This area is the primary cause of traffic problems. Finally, these combined densities will flow together out of the system represented as Q of T. For this model to hold true, we must assume that all vehicles on the freeway maintain a constant flowing distance with a constant velocity of 65 miles per hour.
Ordinary differential equations can be used to model the ramp system for designing feedback control laws. To start, we must create equations for the dynamics of the ramp. The traffic density over a section of highway, delta X, changes with respect to time, delta T. This change is caused by the effective inflow into the section. The effective inflow is given by the sum of the highway inflow and ramp inflow after removing the outflow from the sum. The infinitesimal time limit of the left-hand side provides us with equation 2. In equation 3, equation 2 is expressed as an ordinary differential equation. This provides us with the ODE model of the ramp system with the initial condition of density at time equals 0 is the initial density of the freeway. The objective of a feedback control design is to make the error variable 0. So, as the time approaches infinity, error will equal 0. Critical density is the ideal, the goal for a freeway. Thus, error can be written as the difference of the current freeway density and the critical freeway density as shown in equation 5. Differentiating the previous equation with respect to time provides us with equation 6. In equation 7, we insert the ramp system dynamics found on the previous slide for rho dot of t. The control law for the ramp feedback metering, U, is designed as follows in equation 8. By substituting equation 8 into equation 7, the error becomes 0, and thus the feedback control design is satisfied.
Output without on-ramp. This simulation shows various variable outputs when there is no vehicle input onto the highway via ramp. As seen in the figure, the mainline traffic density oscillates but never reaches the critical or max density of the highway. The mainline will never have a traffic flow breakdown. But due to no vehicle input from the ramp, the queue length, or the amount of cars on the ramp, will keep increasing to an unstable amount as shown in the upper right corner. The mainline and ramp inflow will continue to remain constant, for there is nothing stopping the inflow of both. The control variable of the mainline, or the speed, always remains constant due to there being no input from the ramp. Output with on-ramp. This simulation shows various variable outputs when there is vehicle input into the highway via a ramp. As seen in the graph, the mainline traffic density hits the max density within a matter of minutes, and consistently maintains that max density till traffic decreases before rising again. This is caused by an instant mainline jam from the vehicles entering from the ramp. Queue length will remain constant due to the continuous outflow of the vehicles on the ramp onto the highway. This is shown in the upper right corner as a constant straight line. Mainline and ramp inflow will continue to remain constant, for there is nothing stopping the inflow of both. The control variable on the mainline, or the speed, fluctuates. This is because as cars enter from the ramp, the incoming vehicles from the highway will have to slow down.
Output with feedback control. Feedback control of the ramp meter is directly dependent on highway inflow. The first parameters used to model the feedback control are based on traffic data compiled by Dr. Kaan Utzbe at Rutgers University. The figure on the top left shows that the mainline traffic density reaches steady state, which is the critical density. Subsequently, the error also reaches its steady state, which is 0. The figure to the right shows the inflow of the highway and ramp. As the ramp is metering, it will allow, then stop the ramp traffic when necessary. This is the dark blue patch that you see on the figure. It does this until the traffic dilemma is solved. Once traffic is controlled, the feedback system allows the ramp to flow more freely. Output with feedback control, new parameters. Since the ramp inflow is directly dependent on the mainline inflow, we can take a look at the effects of heavier traffic on the main line. This scenario could be created during times of abnormal traffic patterns, such as a large sporting event, holiday weekends, or alternate highway systems being closed due to construction or accidents. In this scenario, the mainline inflow rate was increased by 10%. The resulting figures show the impact to the feedback metering system. As you can see in the top left, the mainline density approaches the critical density more rapidly and eventually overshoots it. The system reacts to this influx of traffic using the error equation shown in the bottom left. As the system detects an overshoot of the error function, it reacts by initially closing and then opening and then closing the ramp periodically to better optimize traffic flow through the area. These temporary closures cause the queue length, which is the blue patch that you see in the top right graph, to increase and mainline flow to decrease slightly. Once the error returns to 0, The system begins to allow cars on the ramp to flow more steadily, keeping the queue length as close to the constant as possible.
In conclusion, from the initial conditions and models presented, it is clear that on-ramp feedback metering is an effective tool for traffic control. The system works by analyzing mainline traffic flow and computing the optimal amount of time between cars permitted to enter a given section of the highway via an on-ramp. This optimization helps to keep traffic at a critical density, which in turn reduces travel times, increases safety, and decreases vehicle emissions. Thank you.